This is part 2 of the mini lesson on resistive forces, and this time it's a mathematical approach. Let's take, for example, that we have 2 astronauts up in a space station, and they're breathing air. You don't let the helmets fool you. They're breathing the air in the space station. But there's no apparent gravity because the space station is in free fall. So the only force acting on a ball that this astronaut is throwing, the only force acting is air resistance. If we think about a force diagram where this is the point object, the ball, the only force acting is air resistance. Now let's say that it's going very slowly. He's only throwing the ball maybe at like 10 meters per second, something like that, where the initial velocity is 10 meters per second. So that's not very fast, so it's going to be a linear relationship between the resistive force and the speed. And if you recall from part 1, this was one of the forms that the resistive force equation can take. Okay, now what we want to do is use Newton's second law. Sum of the force equals ma. And remember Isaac Newton's form of acceleration, the way he would write it would be dv dt, in terms of calculus. So the first question we could ask is, what is the velocity as a function of time? In other words, v as a function of t. That doesn't mean v times t. That just means velocity as a function of time. Well, to do that, what we need to accomplish is we need to take Newton's second law and set up a good differential equation from that. Okay, so the net force we remember is CV, so I'll substitute that in here, is equal to m dv dt, ma, right? Now let's rearrange it, put it in good differential form, separating the variables so that all the v's are on the left and the dt along with the constants would be on the right. And when we separate the variables that way, we'll get dv over v is equal to negative c over m dt. We have our velocity variables on the left, we have our dt on the right, along with the constants. This will be in good differential format. Okay. Now we're ready to integrate both sides. If we integrate this, we can solve for velocity as a function of time. So we'll take the integral of dv over v from v naught. I don't need to put 10 in, I'll just leave v naught in general right now, to some final velocity vf. Set that equal to the integral. We'll take the negative c over m, that's a constant, we'll pull that out of the integral sign. So that'd be negative c over m times the integral of dt, and we'll just say we're going from a time of 0 to some final time tf. Okay? Now, it turns out that the integral of dv over v is equal to the natural log of v. Okay, and if we're going from v naught to vf, we need to evaluate from v naught to vf. Okay, the integral of dt is just t. Of course, we have that constant in front, negative c over m. And we're going from a t equals 0 to a final tf. Okay, so I just used an integral formula that the integral of like dx over x or dv over v or whatever would be equal to natural log of x or natural log of v. And then evaluated from v naught to vf. So far, so good? Okay. Well, we need to keep on going here a little bit, so I'll just bring in my next page. And when we evaluate, sorry for the paper shuffle, ln, or natural log of v, from v0 to vf, we substitute vf in for v and we get natural log of vf minus, now we substitute v0 in for v, so that's a natural log of v0, equal negative c over m times, we'll substitute the tf in for t, we get times tf, minus, if we substitute 0 in for t, that'd just be minus 0. I don't really need to include that. Okay, now from our rules of logarithms, we know that if we have log of a minus log of b, that's the same thing as the log of a over b, right? That's just a rule of logarithms. So we can apply that here. If we have the natural log of vf minus natural log of v0, that's the same thing as the natural log of vf over v0. And then that's equal to negative c over m times tf. Now, there's another rule of logarithms. It says if you take e to the log of, say, x, that's equal to x. Basically, the e undoes the logarithm. So we're just using rules of logarithms there. So if we exponentiate both sides, in other words, take e to the natural log of vf over v0, and we have to do it to both sides, right? Equals e to this. Well, that will undo the log, natural log here, and we'll end up with just vf over v0. And that'll be equal to e to the this power here of negative c over m t to the f. Multiplying both sides by v0, we get vf equals v0 times e to the negative c over m times tf. If I want to make it a more general equation, okay, we can set v as a function of time, not vf necessarily, but just v. I want to make it more general. Maybe I'm not looking for vf. Maybe I'm looking for some other v at an intermediate time. Well, if I want to find v as a function of time in general, symbolized by v with t in parentheses here, that would be equal to v0 times e to the negative c over m t. So this is the general equation for finding v at any particular point in time. So, for example, if the mass of the ball was 1 kilogram and the drag coefficient was, let's say, 0.2, and we know the initial velocity is 10 meters per second, so if that was the case, then we could actually find out what v would be after, let's say, 4 seconds. So what is v? What is the velocity when t equals 4 seconds? So we could go ahead and substitute that into here, substitute these things into there, and we get the velocity when t equals 4 seconds would be equal to the initial velocity v0, which is 10 meters per second, times e to the negative, and c is 0.2, mass is 1, and t is 4 seconds. These are all up there as an exponent. So let's see if I get my calculator out. So this is a negative 0.8. E to the negative 0.8 is equal to 0.449. So that'd be 10 times 0.449, or 4.49 meters per second. So that's the velocity of that ball after the ball's been traveling for 4 seconds. So it started out at 10 meters per second, and now it's much slower. After 4 seconds of travel, it's only going 4.49 meters per second. So we've just found that we can find the velocity from our basic original differential equation here by integrating both sides, and that's a good thing. Now let's see if we can find another quantity. What if we wanted to find the range at a particular time? What if we wanted to find the range? Well, I'm going to hide some of this stuff here. If we wanted to find the range, we remember that if we take the integral of velocity as a function of time, we'll get the displacement. Okay, so that's good. So we could go from, let's say, if we want from t equals 0 to t equals infinity, if we wanted to find the range over a long period of time. And in terms of our velocity for this particular problem, that would be the range, or delta x, would be equal to the integral of v naught e to the negative c over m t dt. And that looks fairly complicated, doesn't it? However, we can make it look a lot simpler and make it much more doable if we think about substituting a u in for this complicated looking stuff right here. So we'll use what's known as u substitution. We already know from our logarithm formulas that the integral of e to the u du is equal to e to the u. It's kind of like a password. You could get into a math club if that's the secret code word. Say, what's the secret code word? Just say, what's the integral of e to the u? And then your answer would be e to the u. Alright, we know that. So what if we let u be this complicated looking thing right here, negative c over m times t? Then what would du be? Well, du would be just the derivative of that, which would be negative c over m dt. That's easy enough, right? Now what if we solve for dt instead? So let's rearrange and solve for dt. Therefore we get dt is equal to negative m over c du. This is a common technique used in integration. Okay, therefore it's this negative m over c here that's the only difference between what we have here and what we have here. So we're going to need to include this negative m over c, and that's just a constant, in our integral of e to the u du. Okay? Remember, integral of e to the u du is just e to the u, but all we have to do now is remember to make sure we include negative m over c in front as a multiplier. Okay, since the integral of e to the u du is equal to e to the u, but we have to remember to include that negative m over c here, then our final result, substituting back in that complicated value for u, we get equal to negative m over c e to the negative c over mt. Okay. Now, with that, we can go ahead then and solve for delta x, or range. That's just the integral, right? So delta x is equal to negative m over c e to the negative c over mt. and we're going to evaluate it from t equals 0 to t equals infinity. So this is the result. This is the answer for taking the integral of that. Oh, I forgot one thing, and that's the v naught. I should have pulled the v naught out. So we need to have this v naught here also. I'll just squeeze that right in here. Sorry about that. That v naught here needs to be included. That's a constant. Okay. Well, now evaluating for that, we have negative m over c times v naught e to this. Let's go from substitute infinity in for t. And what is e to the infinity? E to the infinity is just 0. So this whole term is equal to 0. Minus, now we'll substitute t equals 0 in for t, a negative m over c times v naught times e to the negative c over m times 0, since we substitute that 0 in for time. And what is e to the 0 power? Well, that's equal to 1. So this whole thing then, right here, would be equal to 1. So we end up with our answer, delta x is equal to a negative of a negative, or a positive, m over c times v naught times 1, or just, this is the answer right here. Okay? So that's a little bit of hairy math for people who haven't been doing integrals for very long. Let me give you an example how we can get some kind of a numerical answer if we were given some numbers to begin with. Let's say the mass of the ball again is 1 kilogram. The drag coefficient is 0.2. Starting velocity is 10 meters per second. If we go ahead and substitute these values into this general formula here, where this is the range as a function of time, we get, let's see, 1 over 0.2 times 10. That's 50 meters of range. So if these are the values and we let that thing go, we'd see that it would go for 50 meters, and it'd take a long time to do that. Okay? Lastly, what if we wanted to find the acceleration of that ball that astronaut is throwing as a function of time? Acceleration. A as a function of time. That doesn't mean a times t. That means acceleration as a function of time. What if we wanted to do that? Well, we know that acceleration is the time rate of velocity per time, right? The rate of change of velocity per time. So we could go ahead and take our velocity, which we found out before was v naught e to the negative c over m times t, and take the derivative with respect to time of that. That looks a little bit complicated, but and then again, of course, we take the constant out of our derivative. That's the easiest way. We'll pull the v naught out of there, and then it just ends up being derivative of e to the negative c over mt dt, or derivative of this with respect to time, I should say. Now, this looks complicated, so I'll just replace this complicated part here with u and do u substitution. So remember from our derivative formulas that the derivative of e to the u dt is equal to e to the u du dt. Okay, just a formula. So therefore, if we let u be equal to negative c over mt, this complicated part right here, we'll let that be u. Therefore, du would be equal to to negative c over m dt. And therefore, if we rearrange, we get du over dt equals negative c over m. So, the derivative of e to the u dt, or over dt, is equal to e to the u du dt, but du dt is equal to negative c over m. Applying this result right to here, and we get that the acceleration is equal to v naught times e to the u du dt, but du dt is negative c over m. We can substitute that in, and so we end up with this. And if we put the complicated negative c over m times t back in for u, then we can get our final answer right here. So the acceleration of that ball as a function of time is equal to the starting velocity times this times e to the negative c over mt. And let's take a numerical example. For example, let's say that we want to find what the acceleration is at t equals 3 seconds. And we still have the mass of the ball 1 kilogram, c is 0.2, and the starting velocity 10 meters per second. We'll take this formula here and just substitute numbers in. So a is equal to our starting velocity of 10 times negative of 0.2 over 1 times e to the negative 0.2 over 1 times 3. This is a power exponent right here. It turns out when we do the math, you get negative 1.09 meters per second. That's the acceleration. So it's not a constant acceleration, is it? The acceleration changes as the ball keeps moving over a longer time period. Thanks a lot, everybody.